Today we're going to talk about building an immune system in Scala. My name is Anatoly Rabinovich, and I've recently become a dad. And my son is a Scala developer also. I've been working at Outbrain for 3.5 years, writing Scala and Java code, mostly Scala. And let me say a couple of words about Outbrain. Who are we? We're a content recommendation platform. You've probably seen our widget on CNN and many more sites. We have 30 billion page views per month. We have 250 billion recommendations served per month. And we have over than 35 million recommendations clicked a day. We're a big data company. So our stack is composed of Jetty, Netty, Spring, Scala, and Java. We use Scala JDBC and Hibernate, MySQL, Cassandra, Elasticsearch, and many more. We use Scala Test and Specs 2 for testing Scala code and JUnit for testing Java code. And that's it, let's start. Our agenda today. We're going to talk about how we were testing code 3 years ago at Outbrain, why it became obsolete, and how the measures we took and the set of tools we've built to tackle these issues, and how we leverage test isolation to solve our problems. But first, what are we testing? It's a microservice. It's Outbrain's public REST API. It consists of many entities and endpoints with lots of flows. These entities are interconnected. And let me give you an example. We have an add entity that is connected to a campaign entity, which also connected to a budget entity. And that in turn is connected to an advertiser entity. And each advertiser may manage many campaigns, and each campaign manages many ads. Okay, so how are we testing? We have DAO tests using real database. We have many unit tests. We had good code coverage. We have end-to-end and integration tests running in a dedicated shared environment we call Simulator. The data required for these integration tests is pre-inserted to the database. And each test uses it to initialize, just to run. And each test is also may create or alter data during the run of the test. So we're testing at scale because we have these numbers are for a single service. 2,000 unit tests, about 1,000 integration tests. Admittedly, it's huge for a single service, and we're working on breaking down. And the funny thing is that no one ever talks about testing at scale. Everyone talks about scaling your services, never testing at scale, and how the scale on the number of tests affects your ability to deliver and to tackle the issues you have with tests, which are getting aggravated with the growing number of tests. But we were confident. We had plenty of unit tests, as I said. We had great code coverage. We had confidence in the sense we could deliver fast, and we could do so reliably. And when I say reliably, what I mean is when you commit a line of code and it passes your test suite, you know that it will always pass the same test suite if it wasn't changed in the future. And we could refactor without fear. And fast is when you could run your CI/CD pipeline and deliver your code, your incremental changes of code to production fast, several times a day. And I think everybody should be familiar with some sort or some version of a CI/CD pipeline. You commit your code, you run your tests. If they pass, you deploy it to your integration environment, simulator in our case. The integration tests run against this new version of code, and if it passes, you can deliver to production. And then we had another environment in production called staging, which was used just to, with some fraction of our traffic, was used to sanity test our code. But not everything was rainbows and unicorns. And I wouldn't have been standing here telling you about this if it was. So what was bad? Our velocity. It was becoming increasingly difficult for us to deliver fast with increasing number of tests, with test run times increasing, and with an increasing database, all of which affected our database query times and the overall test suite runtime. It was taking us more than 20 minutes to just run the integration test suite. I think we got to about 25 minutes. But when delivering many times a day, when we would deliver 5, 6, 7, 10 times a day, small incremental changes, each run of the code of the CI/CD pipeline took increasingly longer. When delivering many times a day, and each test run takes a lot of time, you can see how long CI/CD pipeline delivery time could affect your time to production, could affect the number of times you could take your code to production. Reliability. We had an issue of disappearing data. We had many tests, and each test, my badly written test, could change, alter, or add data that affected other tests run. And any person writing a test could affect my tests. We had a shared environment, right? The repercussions of that were we had flaky tests. And flaky tests, in a sense of, the meaning of flaky test is that you had test failures once in a while. And each test failure, you have to identify the problem, you have to search for the disappearing data, you have to restore it if you need, and all of which affected, again, our time to deliver to production. So flakiness, as I said, is when a test fails once in 1,000 runs, or some other person, some other test alters your data, or some other person thought it to be a good idea to clean some data you used, or is it a once in a blue moon bug which you had all the right conditions coalescing to affect your test suite run this time. And when you deliver to production and you have a flaky test suite, you can't deliver as often. And when you can deliver as often, you accumulate code. And when you accumulate code, you also accumulate bugs. That was the second point, reliability. The third and final point is scalability. Because we had interconnected entities and interconnected data, we couldn't run our tests in parallel. We had to run them sequentially. And running them sequentially is, again, affects your time to run a test suite. So I'll give you an example for scalability and reliability issues. What you see here is a service with two APIs. The first one The first one is create a vehicle, and the second one is get all vehicles, and this is the API we're testing. We have two tests, each of which creates data, and these tests run in parallel, each of which creates data, and then you proceed to testing this API in each test. And each and every test expects it to get one result back, and it may get more. They can't know that. It's an unstable test suite. Okay, so our three pain points: velocity, reliability, and scalability. We proceeded to thinking how could we solve that? What was our light at the end of the tunnel? We wanted to regain our confidence in our test suites. We wanted to eliminate flakiness, and we needed code. We wanted code to be without boilerplate. We didn't want to add any dirty code to our test suites. So the first thing we went after was the long test suite runtime. And the thing we found out, maybe the obvious thing we found out, is that we needed to delete our data. We had millions upon millions of data, of rows in our database, which was unused and undeleted test data. That was just cluttering our database. It was making our test suite slower, and it was making our test unreliable. We started deleting this data on a regular basis. First, I think it was once a week, or then we made it more often, once a day, once an hour. But we still saw it wasn't enough. We still had issues with flaky tests. We managed to improve our test runtime, our suite runtime, but we still had flaky tests. So the next thing we were searching for was, the next solution we took was deleting all data and creating it at the start of a test, class, and deleting it after the test class. What we managed to achieve was a runtime of about 12 minutes. But it still wasn't enough. We still had flaky tests, as I said, and 12 minutes is just too much for us to be okay with. So how we managed to do that? We have a test class, which, as I said, it's an isolated test class. It's isolated from other tests because it generates and deletes its data at the end. So what do we have here? We have a test class. Okay, let me tell you about the API we're testing. We're testing an API that associates a car to its owner. Okay, so at the beginning of the test, we create a person and a car. We use collect GDBC to do that. We override a method called afterAll, in which we clean up our database after. And we have a single test in the suite, which initializes the service, sets the owner of the car using the car and the person we created. And then we proceed to testing the API. We get the person, we get its car, and we compare it to the car we think it should have. It's a nice simple test. And as I said, we have isolation between test classes because each test class creates and destroys its own data. But if I add another test here, I lose this isolation. We may still get two tests running in parallel, which interfere with each other. And we added boilerplate. We had this initialization section at the beginning and the cleanup section at the end. It was better. It wasn't perfect. Oh, I have visuals. It was better. It wasn't perfect. So we proceeded to our next step in searching for our solution. And we use PEX2 scope trait to do that. What we have here, I have visuals here. What we have here is, again, a section that initializes our test data, and we have a method we override called after, which cleans up the database after. And I didn't say that before, but we extend the scope trait, the specs to scope trait, and the after trait. We mix in the after trait to override the after method. What it gives us is a fresh state at each test to be used. We have a brand new person in a car we can use in each and every test. And how we use it is like so. Simple. We have a test class, we have one test in it. We're setting the owner of the car in new context, and we get here a fresh state for each and every test. And then we proceed to initialize the service and set the owner of the car, and then testing our API. And it was clean, it was simple. Was clean, simple, and we just needed to add this new context at each and every test, and we get a new state at each and every test. But it still wasn't enough. We needed some method to share a resource with a test, and we needed to manage it. We needed to manage it ourselves. We didn't want the test knowing about this resource or using this resource, managing this resource in any way. We just wanted the test to use it. And we've started seeing we had bits of code that we repeatedly wrote, and they had a name. And this name was loan pattern. So what's a loan pattern? A loan pattern is as the name suggests, would loan a resource to a test function or to a function. Essentially, it doesn't have to be a test. And the resource should be closed or otherwise managed. Not by the test or the code, it should be managed elsewhere. It removes the responsibility from the developer to manage this resource. And minimizes code duplication. And then let me show you how we do that. It looks like so. You've probably seen this piece of code many times in your code. You've probably done that a lot of times. We have a handle file method, which gets a file parameter, and it gets a body to run. At the beginning, it initializes the file input stream, then executes the body, lending it the stream, and finally it closes the stream. And how we use that is calling the handle file method with new file, and at the body we can write anything we like. We can print the lines of code, use it, parse it somehow, anything you want. And as it turns out, our testing frameworks offer us a built-in solution, a built-in way of using and implementing the loan pattern in our tests. So, how does it look? A bit more code this time. We have the first part. We have the test data support context trait, which implements a single public method. It gets a test code body. It's initializing test data. The test data in this example is default objects, which contains a car and a person. It then proceeds to executing the test code and lending it the test data. And finally, it closes, it clears the data it created. So we can make it generic. We can use T instead of default objects, and then you can use it in any way you like, with any data you like. And how we use it in our code. We have the same test class with the same test. We set the owner of the car in test context. It's the public method we used. And then we have the test data available for us inside the test. And we initialize the service, we set the owner of the car, and we set it using the data contained in the test data. And then we proceed to testing our API. So it was a simple way of doing that. If you look at it side by side, this is the old version and this is the new one. We removed all the initialization part from the test class to an external trait, and we added the in-test context using the test data. So the difference between these two tests is that essentially this test is not isolated from other tests, and this one is. Let me show you how it looks in Specs 2. I've taken this example from the Specs 2 documentation. What you see here is a similar trait called database context, and it extends the for each trait, which is the way to do that in Specs 2. You then implement the for each method, initializing the open database transaction, initializing your test data, calling and executing the test, giving the transaction, and closing the transaction at the end. It looks very similar to the Scala test example. And you use it by just mixing the database context trait, and you just get the data. You get the data at the test to be used however you want. So what did we achieve? We have our confidence back. We run tests in parallel due to the test isolation we implemented. We have the tools now to write isolated tests. And we have our velocity back. Our test suites run, I think, about 4 minutes. And we reduced boilerplate, or we didn't add boilerplate to existing tests.